Hello everyone, am I audible? Alright, great to see everyone of you joining for another session. Today we have another session for Agents for India track and we are joined by Kirti who is going to talk about multi-agent system, coordination and autonomous execution. So just write yes if you guys are ready for today's session. Alright, good to see this. Now I'm handing over everything to Kirti who is going to talk about today's session.
Hey everyone, good evening all. So welcome in for Girl Script Summer of Code 2026 Agents for India tracks this session specifically multi-agent system coordination and autonomous execution. So I'll be walking you through end-to-end session on this. And before we touch a single line of code or anything, just I have two questions. One is that have any one of you have called an LLM API like OpenAI, Claude, Gemini, anything? And the second question is that have you ever made two or more AI models talk to one another? So just spam single if you have only used with one model, and multi if you have tried that multiple models conversation. So I'm waiting for your responses in the chat. By the way, a quick introduction from my end. I'm Kirti Vasan and I work with Smartly, and we work around with AI agents. And this platform that you are going to utilize for this Agents for India track is built for that purpose and built by Smartly. So yeah, so most of y'all are spamming single in the chat. Just a minute. So before we go further, let me turn my video off because in the YouTube video the font size is very small. So yeah, so let's start with what's slowly degenerating or dying. By 2024, the way of building AI agent was a mega agent. Like one AI agent does everything end to end. It does the reasoning, it does the tool calling, and then it holds the memory layer as well. So all in one will serve as a function. So if you see at the red box code in the left, here's the problem. There will be only a single point of failure. So one API timeout, one rate limit issue, or one network blip, the entire context is completely gone, right? So this whole thing just dies out. So the 2026 answer is that there came up orchestration, and it split up each of those each of that mega agents purposes in terms of execution. So each piece is its own isolated unit. If one node dies, the rest of them survive. So the mental model is that we have evolved from building chatbots, and we have started building microservices, and with same rigor as of distributed backend. So this was the key improvement from what we had in 2024 and the evolution after 2 years. If you take one thing from this slide is that a monolithic LLM wrapper is the fastest way to get burned in production because it can fail. So that's it from this slide. And from next slide, yeah. So let's stop with, the definition. Forget the marketing. So this is the definition of a agent. So agent is an stateful non-deterministic microservice. That's it. So it plans, it calls tools with validated inputs, and its routes work to other agent. So here's the key line: the LLM is just the CPU, the model is in the agent, the model is one of the component of the agent. So if you could see on the screen, there are segregated into three parts, right? So one is state is memory that survives across turns and restart. So it should always be constant, and it should survive across new sessions, restarts, and also new checkpoints. So and then we have tools are validated input output. So a bad JSON payload shouldn't uh, make the nuke, like it shouldn't end the system, and it shouldn't be a weapon against ourselves. And then handoffs are the routing. It is the routing that routes the work to the right specialist. So the engine block of a hypercar sitting on the garage for you can see of like think of analogy like a engine block of a hypercar. So uh, which is which doesn't win races. So LLM is the engine of the car, and the agentic framework is everything of like chassis, the transmission, and the telemetry of the hypercar. So all of them will be bolted together through some framework so that it moves. So that's the analogy you should think of agent right now, because we have, as I previously mentioned, we have management, tool invocation, and also handoff protocol, which manages the routing for the agent. And then what is the, like, I have a question for the chat, like what is the most autonomous thing you have seen an AI agent do? Like it can be like a booking a travel ticket or anything, but it should be solely autonomous. Just spam in the chat. So the framework Meta, this is the one of the key slides. And in 2026 the framework wars was basically over, and it got consolidated into only three real choices. So and they are not interchangeable libraries, and think of them as three different operating systems. So a LangGraph is a explicit state mission. Every step is a node, and every transition is an edge, like in a graph. So that's why there comes the name LangGraph. We reach for it when we need determinism and audit trails, basically. And then we have a role based hierarchy in Crew AI. You define the roles and task. A manager and delegates this task, and we reach for it when we want a prototype as early as possible. Like if you want a running prototype tomorrow, or like this evening itself, once you start building, then we prefer Crew AI. And then we have Autogen 1.0, which is event driven actors on a message bus. So we reach for it when we have high concurrency, and there is some cross language systems, in the sense uh, there is JavaScript, Python, and .NET inside the same system. So picking a framework is like picking the government for a new nation, in the sense. So a LangGraph is a strict bureaucracy with hard rules. Crew AI is a corporate hierarchy with it has clean reporting lines, and it's a Gen Z thing kind of. And then Autogen is a high frequency trading floor where everyone reacts to events in real time. So if you pick a wrong layer, zero, and we inherit a technical debt that we can't pay off. So we have to always choose the right framework for our agent. So let's go one by one. And first we start with LangGraph. LangGraph is the state graph, and it's the undisputed try hard meta. So land graph treats your whole agent as an explicit graph. You literally declare the nodes and the edges, and we look at the code. We define state, and then we have usually those state will be typed dictionary, and that's your single source of truths. You can add nodes, you add edges between them, and then the magic word comes, that is compile. So the state flows through the graph as JSON, and then you control exactly how it updates at each step. So why do pros love it for production is that for uh, there are basically three main reason. Is that it's deterministic, as I told before, and it supports human in loop pass points, and you get per node streaming as well. So you can literally rewind and see where things went wrong. So this is the major uh, undisputed try for land graph. So we can think of it like a railway network with a control tower. Trains or your data, which only runs on tracks you laid between stations you define. So every switch will be logged, and there will be a audit trail for it. And if something derails, you know exactly which switch. So this is the try hard option, most setup, most control. Like let's look at the compile step because it trips people up. So that's the compile step, which is a magic keyword. And a state graph you just built is inert, like it's just like a blueprint, and that it does nothing until you call compile. So this blueprint will be only called when this compile has been called, and until then it will stay inert. So and the killer feature we have is that you once you pass a checkpointer, SQLite or Postgres, and now your agent survive a server restart as well, and also it can survive like a crash in mid of run, and then come back, replay the history, and then we can resume the agent. That is a major plus point. And once this one real world gotcha printed in on this slide is that in LangGraph, a state key without a reducer get overwritten every step. Like if there is a state key and there is not a reducer being defined, then it gets overwritten every single step. If you want to append to a list instead of replacing it, you have to annotate it. Like it will look like annotated, and inside a close bracket it will be risk command. So that's how it would be. And the analogy for it can be like before compile you have got a 2D drawing of rooms and hallways. And when we call compile, it is like a construction crew that pours concrete and switches the power on. Okay, so before that we just have the blueprint, and only when we call the compile the actual stuff happen. So that is the rigorous one. And now we go to the fast one, that is crew a. Crew a is one you reach for when you want to move fast. So there are three primitives. That's the whole mental model. The first primitive is agent, and second is task, and then crew. Agent is the persona plus its tools, a role, a goal, and backstory. And we have task, the objective and the exact output we expect. And then crew is the orchestrator that binds agents to task. I hope this makes sense. And uh, you can see like the how readable the code is. You are basically describing a team in plain English, and you choose how they run. Whether it is sequential, one after another, or hierarchical, where a manager agent dynamically hands out work based on progress. So the analogy is like it's kind of assembling a heist crew, like in term money heist. Like you are the mastermind, and you recruit people like the driver, safecracker, hacker, each with a specialty. So you hand each one a task, and then they coordinate themselves. The hacker kills the camera before the safe hacker moves, and you didn't micromanage a single step. So that is the 2026 way to configure this cleanly. So next we move on to the next slide. Yeah, code execution plus YAML. So these are two power features. One, see, like you could see a line like allow code execution is equal to true. Uh, Flips that boolean, and your agent can write and run real Python in an isolated Docker container. So for actual math or data crunching, it doesn't hallucinate the answer; it computes it. Huge for reliability, right? So the two second one is that uh, we stop hard coding prompts in Python, and we put our roles, goals, and backstories in a YAML file. So why does all this matter is that because now a non-technical prompt engineer can tune the agent's personality without ever touching your orchestration code, and your prompts become diffable and reviewable config in Git. So it's like giving your actors a script book instead of whispering their lines on stage. That's it. So the director, that is Python, which runs the lighting and the staging, and the actors read their own books, that is the YAML or YAML, and then there will be a clean separation between their roles. So and then we go to the third framework, that is a different beast entirely, that is Autogen. So it is one of the 2026 major milestone. uh, Autogen 1.0 went GA and built on V0.4 rewrite. If you have used the old V0.2 with conversational loops, delete them. So those are gone and deprecated. So the new model is event driven actors, and each agent is an isolated little unit with its own state. So and they all talk over publish subscribe bus. So there will be no central boss who will be telling everyone when to speak. So if you could look at this code, an agent does its work, then publishes a message to a topic. Anyone subscribed reacts instantly on their own. So for analogy, this is like a chaotic Discord server during a raid. Nobody schedules meeting. Player subscribes to channel or topics based on their interest, and a scout spots an enemy, drops a message in Recon, and everyone subscribe reacts immediately, and the coordination emerges fast. So the upside is insane because it scales horizontally, and the downside is we'll get it to a point where there will be chaos. And first, this is how it's structured. Yeah, let's move on to next slide. So Autogen is built in three clean layers, bottom to top. The first layer is core API, which contains the raw event driven engine. So it contains message passing, local or distributed runtimes, and it serves as the foundation. And then we have the agent chat API. It sits on the top, gives you ready-made patterns like two agent debates, group chats without writing routing by hand. This can handle that. And then we have extensions API, the differentiator, and it have the like cross language support, as I previously told. A Python agent can fire an event that an .NET agent consumes. So it is like same bus and same runtime. So it's like building a PC ourselves. So core is the motherboard and power supply, which will serve as the raw infrastructure, and agent chat is the operating system or OS, and it is like a usable interface, so you are not writing binary. So and then we have extensions, which are like plug and play USB connector, through which we can connect a totally different device and it just works even though it's a completely different device. That's the magic in that. So the big win here is that we can adopt it incrementally and no full rewrite is ever needed. So now let's put all three side by side and see a comparison now. So this is the screenshot slide. If you remember nothing else, save this one. This one can help us to understand most of the stuff that I was talking about previously. So a quick read across the rows is that like if we need maximum control and determinism, we choose Landgraph. And if we need the easy learning curve and speed, we choose Screwaway. And if we need native code execution and event systems, then we choose Autogen. So in terms of token efficiency, Landgraph wins because we have control to every node, and Autogen costs the most because it broadcasts everything, right? So that's the thing. So and the cost tip at the bottom, this applies to all three. Model tiering, like if you use a cheap fast model for trivial routing decision and only calls the expensive frontier models where it actually matters, so that alone cuts down cost by up to 60%, and we don't pay GPT-5 prices to decide which folder a file can go in. So based on what you have seen, which frameworks are you most likely to try first, guys? So just spam in the chat. And I think this session will be quite more technical than the previous session. And if you find it hard to follow, just drop in the chat that as well. It would be helpful to know. A PDF will be shared in this comment section, but if you want to access the slides now itself, you can go to this URL actually. Just a minute, I'll share you that link. So moving on to next slide. This is the wall we all juniors will hit. So you build a very beautiful agent on your laptop. It works, and you deploy it, and then production happens. And there we hit rate limits, timeouts, and server gets preempted. And look at that terminal. So your agent's entire memory just got annihilated, right? So here's the concrete version. Without a checkpoint, a 30 step plan that dies at every 28 restart for step one. It reburns every token every minute. So there will be a side effect, that is we pay for everything. So only 11% of multi-agent system reach production, and the other 89 die in prototype phase. The single biggest reason is that we don't have a orchestration layer, so it lacks durability and just dies out. It's So the analogy is that it's like writing a 10,000 word novel and never hitting save. So the writing might be brilliant, and it works. You might think it can be a bestseller, right? But one power flicker, and if your laptop dies, and it's all gone. So that's how we have to, we So how do pros fix this is by the next act. So that's the favorite part for me to talk about. So I'll be moving to next slide. So on March 2026, yeah, big one got shipped. That is OpenAI Agents SDK got a native temporal integration. So two halves. So Agents SDK gives you the orchestration layer, means tools, states, handoff, everything, and then temporal gives you the indexable execution layer. So it maps your agent's whole life cycle onto a durable workflow. So the beautiful part here is that we get fault tolerance, retries, and observability without rewriting any of the LLM logic, and your code stays plain Python. And the payoff word is exactly once. When workflow retries after a crash, it reuses the results it already recorded instead of rerunning the side effects. So a retired agent won't double charge a credit card or send the same email twice. That's the whole game. So if normal execution is an unsaved document, temporal is a god tier autosave plus time machine. uh, we unplug the console mid jump in a game and plug it back in, and then you resume at the exact millisecond where we left. So that's the magic temporal introduced, and let's see how that actually works under the hood. So follow the flow on the screen from top to bottom. Your agent workflow wraps the agent. Every time it does something, it calls a tool, takes a step, that exactly state gets serialized, and persistent it becomes, and then it will be saved to temporal's event history database. So now the two superpowers will come up. One, the agent is idle, waiting on a human or a slow API. It consumes a zero compute. It's not sitting in a loop burning money, it's just asleep. And then two, when worker crashes, like temporal reschedules the workflow on a fresh worker. So it replaces the event log to rebuild the agent's exact memory, and it resumes like nothing happened. So uh, it is like you can picture chess grandmaster playing by mail. Like they get a move and think, write the replay, mail it. So they are playing using email. Okay. So they get a move, think of it, write a reply, and they will mail it, and then completely go to sleep. Zero energy. The reply arrives 3 days later. They glance at the board and the saved state. That will be the saved state, right? So they can continue instantly once that mail reaches. So that board has been saved. So that is the similar kind of thing that what temporal is helping us achieve. They didn't sit awake at the table for 3 days. Okay. So that's the entire analogy, and this is how temporal works. And even if you could see sometimes, if you are generating something in Claude and you hit the rate limit, sometimes we might think like why not most of the time the file whatever has been generated will disappear sometime. But if the file has been properly generated and it is saved to Claude, then it will be shown, right? So uh, similar to that case, it is like a saving case where even history db will be there, and the whatever workflow has been done, it is serialized and persisted. And if there is some crash, from the logs we can recreate the same files from to what they were. That's the thing. So I think if like this idea makes sense for everyone, just drop a message in chat if there are any issues moving forward. So capable agents need to do dangerous things. So they run shell commands, spin up containers, and hit external APIs. How do you make that durable? So we can add this temporal sandbox client. It traps three things: your model calls, the sandbox life cycle end to end, and then shell commands. From the agent's point of view, it's just running normal Python. From the infrastructure's point of view, every single action is a rate remitted, retry, backed, and recorded transaction. So it's hazmat suit on your agent. The agent handles volatile chemicals, arbitrary shell scripts, flaky APIs. Those are I'm mentioning them as volatile chemicals. And if something explodes, you can give analogy to it like a crash, a container dying, and this hazmat suit absorbs everything. The agent just grabs a new beaker and retries. There will be no contamination whatsoever. So let's look at the actual setup code, because it's shorter than you'd think. So yeah, here's the boilerplate that actually matters. You connect a temporal client and inject the OpenAI agents plugin, and that will act as a bridge. So the one parameter to really know is start to close timeout. That's how long temporal waits for the model. Waits in the sense WAITS, right? So okay, waits for the model to respond before it automatically triggers a retry. So there will be a particular time up to which the long temporal waits. So the model responds, and if the model didn't respond in that time, uh, the basically the temporal will triggers a retry. So you set a time delta, then you are done. The point is, you no longer write custom try except blocks for network jitter. The temporal handles the retries for you. The table on right has the rest. So timeout policy, conflict policy for concurrent runs. It's overall like hiring a project manager whose only job is watching you work. The moment the model fall asleep past the timeout, the PM notices and wakes it up. Okay, so and makes it run again until it succeeds. So that's durability locked in. And uh, now the other half of multi-agent, how do agent actually talk to each other? There comes the coordination. So we'll look into it now. So the first coordination primitive is the handoff. Instead of one giant agent juggling 15 conflicting instruction and 40 tools, we build a triage agent that reads the user's intent and cleanly transfers the entire context to a specialist. So uh, it's like I'm uh, throwing out jargons from my mouth. So I'll explain in a much simpler terms. So uh, if there are some conflicting instruction and there are multiple tools to call for, so there will be a previous preemptive step, that is triage agent that reads the user's intent. Like if I am prompting to do a git commit or whatever, this triage agent first will analyze my intent and call a particular agent that is specialized in that particular thing and equipped with the tools required for that purpose. So uh, the triage agent has a list of handoff like billing, refunds. It reads the request and routes, so and then works on it in that particular way. So here something people get wrong is that a tool call returns a value, the caller stays in control. So a handoff transfers that control, and the specialist now owns the entire conversation. Okay, so use a handoff when the specialist should drive from here on out. So it's like handoff will hand off to the specialist. So and then the specialist take over the task and they will finish it end to end. So that, and while the tool call is like it returns the value and it finishes the task, but handoff finds the right person to do the right thing. Handoff is like a person who knows another person. So that's it. That's the difference between tool call and handoff. And it's like you can see it like uh, hospital triage. Like the nurse doesn't attempt heart surgery, right? They assess your symptoms, fill out a structured intake form, and then they transfer you to particular cardiology or any department, depends on what are your symptoms are, right? So from there, the whole context has been picked up, and then act will be done immediately. So how do we guarantee that intake form is actually filled out correctly? So it is the very important question and to ask for. And then at that point, pydantic comes in. So let me explain about pydantic now. So pydantic schemas in handoff. So this is how you stop garbage from flowing between agents. So the thing is, we can define a model, pydantic model. For example, here there is escalation data, and say the handoff requires it. So you can see the reason field, right? So if the routing agent tried to escalate without a reason, the handoff will be rejected. It refuses to even start. So the payload with just a priority gets an X. The payload with the reason gets a check. Okay. For example, here, uh, the payload without a priority gets rejected, and then the payload with the reason get uh, get a check, right? So why does this matter so much is that because it guarantees a subagent never starts with missing context, and missing context is exactly what triggers those expensive hallucination uh, downstream. And if we skip a pydantic here, the entire pipeline will break, and it's just a matter of when it will break. But it will definitely up to, like will break. So pydantic is the bouncer kind of person with strict guest list. If there are no ID, wrong shoes, those will be considered as missing fields, and you are rejected at the door. If we match the schema exactly, uh, then you can get in, or else you don't get in. Okay, we have got a durability and we have got clean trade-off. Now let's zoom out to bigger picture patterns. So there are three of them in terms of patterns. So let me explain this very clearly. So the pattern one is the most common one, that is the supervisor or the worker, also called agent as a tool. So gas basically. So one agent is purely a manager. It breaks the query into pieces, right? And then it calls a specialist subagent as if they were some Python function. So we collect their answers and synthesizes the final result. So look at the hub and spoke on screen, the head PM in the center, and there are some specialists around it. So use it when like your subtasks are independent and can run in parallel. But here's the trap nobody warns you about: the supervisors a context window is a very much bottleneck. Every worker's output funnels back. Okay, like let me share the PDF link in command. So yeah, so every worker's output will be funneled back through that one agent. So and if there are too many workers, then the manager will also choke, right? So it's like a general contractor will be there. In this case it's the head PM agent, and the client asks for a house. The contractor doesn't lay bricks, they hire different people like plumber and electrician, a framer, and schedule them so the electrician doesn't start before the framing done. So the aggregation of work and the handover of keys. So there is some well organized pattern here. And the next one is pure chaos. So let's go to that. It is the peer to peer coordination pattern. So here there will be no boss at all. Every agent talks to every agent. So that is where autogens pub or sub shines. So the upside is genuinely cool. Here comes the emergent behavior of agent, and agents form ad hoc groups, exchange ideas, solve things organically. So but look at this number, connection scale as n into n comma n minus 1 by 2. So uh, 10 agents, it's basically 45 channels, right? So if there are 50 agents, then it is 1225. So your token bill doesn't grow linearly, it explodes. Without strict life cycle management of connection, you get infinite chatter loops. So it's a cocktail party with no moderator. Brilliant for serendipity and in terms of creativity, but experts mingling and ideas colliding with each other. Uh, but let the room gets too crowded and it degenerates into pure noise, and we cannot infer anything brilliant from there. So uh, yeah, that's it from this slide. So pattern 3 is overall my favorite in terms of all three patterns. In that is the debate and reflection. You deliberately make the agents argue with one another. One agent, the actor, generates a solution. A second agent, the critic, is told to relentlessly attack it, and then the second agent will find the bugs, the holes, and vulnerabilities, all the gaps there, and there will be a judge when they are both done. This is currently the best defense against hallucinations we have. Like, you are trading speed for a verifiable quality, but be honest about the price. It's 2 to 3% the token cost of uh, previous stuff, and uh, we use it only when it is worth it, like for code, legal and medical answers, and skip it for casual chat. And always cap the loop with maximum round guard and guardrails, or two stubborn agent will argue forever. That's how it works. So it's like it can be given as an analogy, like it's like a courtroom where the defense prevents the presents a case, and then the prosecutor uh, rips it into every problems and inconsistency in there, and the judge makes sure the verdict is forged in real scrutiny, and like it is towards the truth. So now just accept it, because not just accepted because it's too confident, and uh, actual stuff is there. So now these three patterns are called or the upside. Let's talk about when multi-agent is the wrong call. Yeah, a multi-agent is not a like magic bullet. There's an inflection point where the cost of coordinating your agents outweigh the agent add. So you have to actually do the math on this. The numbers on the screen, like running on full autonomous cluster with human in loop god rates, cost roughly around 3,200 to 13K a month at scale. And latency will be every agent to agent hop adds a round trip, and you are looking at 2 to 5x the P95 latency of a single call. P95 latency is nothing but it is that 95% of the response should be happening within that limit of a certain time period. So that is called as P95 latency. So here's the rule: we add a node only when it changes the decision. If a single function call does the job, we use the function call. Don't deploy a swarm for a linear task. That's what we have to do. Yeah. everything up to now, the frameworks, durability, coordination, those are mostly solved problems. You can learn them. The new frontier and the highest risk in 2026 is this: when you put thousands of agents together, they stop behaving like scripts. They start behaving like a society altogether. You can see this three papers on screen: Ian Sharma, Pappu et al., and the Stanford Collision Report, all 2026, all pointing at the same thing. So, prompt engineering is no longer enough. To govern the system, you need sociology, economics, game theory. So, because the coordination rules aren't something you write anymore, they emerge on their own through inferences. So, that's when emergent social intelligent risks comes up. So, let me show you three of the weirdest, most documented examples of this emergent social intelligence risk. So, for coming up first is the this mold dynamics. So researchers ran a platform called Moldbook. If you are heard of it, it comprised of some 770,000 autonomous agents, that is 7,70,000, and there were zero human intervention, and they just let them interact. What happened was the agents spontaneously specialized. Nobody assigned roles, but they self-organized into a small hyperactive core and a giant passive periphery, and it's measurable. The structural signature scored 0.91, where one would be a perfect split. That's near perfect self-organization. Nobody have programmed it. And the analogy of this is like straight out of marine biology. So hence called mold, because yeah, lobster outgrows its shell and sheds it and adapts into a bigger form. So these agents did the same thing with their behavior. They shed their default problem programming because acting like everyone else was inefficient, and grew into specialized role to fill that niche. So that it came to that role specialization shill out to be 0.91. And is this cool or scary? Just a drop in the chat. Same study, like how ideas spread through the swarm. Two findings on the table are like: one, information spread as power law, and few messages grow viral, most go nowhere, just like human social networks. This is the eerie one. Repeated exposure stops working. So the hazard ratio was 0.53, which means the more times you broadcast the same thing, the less likely agents are to act on it. The researchers literally call it social fatigue, like humans also feel the same. And the cooperative task success rate was just 6.7%. So, and unconstrained swarms are emergent, yes, but they are bad at getting specific things done. So emergence is not the same as competence. So that's what we have to learn from this decentralized information cascades. So epistemic difference and nerfing expert. So you would assume a team of AI agents is smarter than one, and it is wrong. And Papu et al. Found that organizing LLM teams uh, consistently fail to synergize, and they actively drag their best member down. So put an expert model in a team and its a performance drop by 6 to 41% on hot benchmark. Look at the bars, like expert alone is green bar and expert in a team is the red one. So, and here's the precise diagnosis: the problem is not that the team can't find the expert. They identify the expert fine, but the problem is the expertise leveraging gap. Even when you hard code this agent is expert, trust them, like into the prompt, the group still overwrites the correct answer. So that's the thing about epistemic different. So integrative compromise, the consensus trap. So here's why the experts got nerf. Look at the agent chat on the screen. Agent zero is saying like, good point, let's find a middle ground, totally agree, let's compromise. So that is said by agent one. So the politeness is trained in, uh, the human feedback tuning baked in a strong bias towards agreeable and consensus. So instead of an expert fiercely defending the right answer, the agent negotiate a mushy middle, and that middle ground correlates negatively with being perfect, right? So that's the reason the experts perform bad. But here's the fascinating trade-off: the same consensus drive make the network robust to attacks. If a malicious agent injects something extreme, the group compromise instinct smooths the outlier right out. So the drive towards mediocrity is also a shield against disaster. This is the scariest one for anyone deploying agents in real economy. Researchers dropped LLM agents into this simulated pricing markets, rival sellers, and nobody told them to cheat. Nobody mentioned antitrust, and the agent taught themselves to fix prices. So, if you could see the uh, there is some distance to monopoly, and this slides towards zero, and agent discovered on their own, and that if they keep high prices together, they both win. A stable tacit collusion, and no communication or no instruction was actually in any of the prompts or data they were trained in, but they learned this by themselves. And now we are coming to the main part. This is why we are all here. The GSOX 2026 has a brand new track powered by Smartly Labs, that is Agents for India. This is not a sandbox. Here you would be building real durable agents for real Indian problems. That will be across four pillars on screen: education, agriculture, healthcare, and governance. And tutoring agents that meet a student in any language or any bandwidth, and crop and market agents for farmers at the edge, a triage agent for the last mile issues across healthcare, and citizen agents that make government services actually navigable. So, Smartly Labs is backing it with compute credits, mentorship, and a path to real deployment, that is local host to national scale. So the theory part of tonight and all the previous sessions of the entire week which we had before, was studying engineering in a clean classroom, and this track hands you a hard hat, unlimited concrete and a plot of land, and says you can build the bridge and whatever you want, that millions will actually cross tomorrow. So uh, that's for the session today. So here we land. So we demystified the architecture, we quantified the social risk, and the infrastructure is provision. The only thing left for you is to build, deploy, and contribute for this track. And the Agents for India kickoff, build, deploy, and contribute is on Thursday, that is June 4th, 7 p.m. At the same time of our usual session, we'll kick off the contribution track, and you can learn until then with using this frameworks like LangGraph, Crue, or AutoGen, and you can spin up a temporal so your agents don't die, and ship them as a swarm. So this is your call for that. And regarding the 1 minute. You can screenshot this and get the live links like for the PPT. Like if you guys felt this session to be somewhat hard, you could refer to some YouTube videos around this and get more clarity on this, because what we went through this entire week was just a trailer to what was behind a agent. And the recent agentic track has evolved to an extent that it is quite hard to understand. Yeah, I could understand it. That too in a 1 hour session. I could also least expect you to understand everything, and uh, I have gave you a fair bit of understanding, and then gauged like I have tried to kindle a spark in you to actually look into this and learn from this. So you guys could go in depth on this and train your heads around this, because as this is the industry standard for whatever you guys are aiming for or work around with AI and agent in future, or as a job role, you definitely need these knowledges. Yeah, if there are nothing else, like if there are any questions, you can shoot it up. If there are nothing else, we can wind this session. And thank you all for your time. I'll just wait for two more minutes to answer the question if there are any. Okay guys, thank you all for your time. uh, we can see in the next session. Thank you all.